Okay, so hi. Every single tree problem you will ever solve, diameter, balanced tree, path sum, lowest common ancestor, or any of them, all of them are built on top of one idea. And if you understand this one, you don't just solve LeetCode 104, you unlock the entire tree section. Okay, so let's slow down and actually derive it instead of memorizing it. So, what exactly is a binary tree? This is the main question. It's a new topic for you guys. Yep. Okay, so what is a binary tree? A binary tree is just a node with at most two children, like three has at most two children. It can have one children, but at most two children, which is here 29. Okay, a left child and a right child. Okay, so that's it. Each node points to a left and a right. Either one can be null or it can have a value. Like 9 have both the values as null, 20 has both values as something. Yep, and if 20 had only 15, it would also have been a binary tree, and the second one would be null for that case. Okay, so what is maximum depth exactly? So, maximum depth just means what's the longest path from the root down to any leaf. Like it can be on the left side, it can be on the right side, right then left, right then right, any path, but the longest path. Like in this tree, if we can see, the longest path is 3 to 20 to 7 or 15. Both are both have the depth as 3 3 1 2 3, right? So yeah, so brute force thinking, what they are able to think. Let's move to the whiteboard first. Let's move to the whiteboard. So yeah, here is the tree. Okay, your first instinct might be, let me just look at the whole tree and count, right? Like 3 then 20 and then 15. Yeah, but the computer can't just look, right? It can only stand at one node. Like assume that we are standing on 3, and then it can ask you, what do I know from here? Like it doesn't know he has to go to left or to right. It doesn't know, right? So standing at the root, here's the problem. You don't know the height of the whole tree, right? You don't know the height. But wait, do you know the height of the left subtree? No, not immediately, right? You have to go first to 9, and then if something is there also, then to, if right subtree is there, then you have to go to 20 and then 7, then you can find the height, right? So standing at 3 you cannot find. Okay, so what's left to do? So here comes in action recursion, right? I hope that you have heard some of the part. Like recursion just means like calling a function recursively means again and again, and like in the same function we call it multiple times. We call the same function multiple times. You will understand that shortly. Okay, so here's the trick. You don't need to know it immediately, you just need to ask. So ask your left child, that 3 is asking 9, that what's your depth. Okay, and then it asks the right child, what's your depth. And here's the beautiful part, each child asks the exact same question to its own children. Like 20 will ask it to 15 and 7, and 9 will ask it to the null pointers it has on the left and right part. So this keeps happening until someone reaches a null pointer. Okay, like which node doesn't exist. For like for 9 it is the case that if 3 asks it left node, so it does not have to be anywhere because its both nodes are null pointer, right? But in case of 20 it has to first ask to 15 and then ask to 7. Okay, so the base case is, okay, so in recursion we need a base case. What is a base case? Base case is just like where the recursion must stop. Okay, otherwise it will become an infinite loop. So where the recursion should stop, it is the base case. So base case in this question is that both the pointers become null. Okay, so this is called basically like DFS, depth first search. So once both children answer back with their heights, what do you do with that information? You take the bigger of the two, because the deepest path only goes down. Like if 20 had on this left side 15 only, and on the right side it had 7, and again it had something like 2 or something like this. Okay, so then the height would be max of this 2 and this one, so 2 would be here, and then again max of this, and we will go like recursively to 3 then. Okay, so we have this for now. Okay, so we take the bigger of the two, and then we add 1 also, because if we are standing at 20, so yep, we had to add this 20 also. So to get the height, basically this should be there only, and if there was 2, so 2 here and plus 1 of 20, so the height would be 3, right? like this. Height would be 4 because 3 should also be added because it also counts in itself while taking the max of 20 and 9, right? So it goes on recursively, like 15 gives a value and 7 gives a value. We take the max of both, and then 20 has a value, and 9 gets a value from here, left side. So these 9 and 20 give their max values to 3. So, and at every step plus 1 is going on because it needs to add itself also, right? Okay, fair enough. So notice that we didn't start with this formula, like we arrived at by asking what does each node actually know. So formula would be, we can say, like, okay, so if we talk about a node, depth of a node, right? Depth of a node, if we talk about this, so the depth would be of a single node. Like if we talk only about 20, only about 3, for this we would take max of left depth and right depth, right? Because just a sec, it's depth, okay, yep. So depth must be like 1 plus, because we need to add 20 also, and from these left and right we get the depths of these, so add plus 1, and for 3 we get from 19 and 20, 9 and 20, and then we add for 3 plus 1. So this is the, like, this is the condition in the recursion. And if we move to the dry run part, if we say the like dry run for this, so let's try to run it. We'll just erase these extra arrows and then we will move to the code part. It's not that hard because it's a basic tree question, it's just the base of every question. So yep, so if we do the dry run, so assume we are at 3 and we are going to calculate the max depth of 3. So what it should do, it will ask 9, do you have your max depth? 20, do you have your max depth? They say, yeah, we don't as of now. So it moves to the left first, 9. Okay, so now we will do same recursive call for 9. 9 asks us left pointer and right pointer, that you guys have your max depth or not. They are null pointer, so to say yes, we are null pointer, we don't have any problem. We have the, like, you can say, like, our max depth, if it call the max depth for null pointers, they will give 0, all right. And if the function then it will come back again, right? So at 9 what it will come, 1 plus 0, because max of left and right is 0 because they are null pointer. So here it will come 0. So here we have, as of now we have 1 value because we add, okay, my bad, okay, here we have 1 as the value, okay, yeah, 1. Now let's move to the right. Okay, these were null. If I write for your convenience, these were null. Okay, I am representing x for null. Okay, so now we, like, if the node, like, if any node gets its left depth and right depth, it can move to this formula. Okay, so 9, my bad, so 9 had its right and left both at 0, so we move to this part of the formula part. Now for the right subtree, if 3 asks 20 that you have your left and right max depth, it says I should ask them. So 20 first asks 15, 15 says yes, now I have, because it's null here, null here, so now it has. So 15 gets 1 because 0 0 and plus 1, and 7 gets again 1, okay, and max of 1 and 1 would be 1, and 20 would get 1 plus 1, that is 2, okay, and 2 of 1 max would be 2, and 2 plus 1 would be 3. So that's how we get the max depth, right? I hope you got the dry run. First we asked for left and right, that left and right, do you have your max depth? If they say yes, then we move upwards, and then if say no, they have something below them, so we move below. So this was basically the dry run. This is the optimal approach of this question. Now we will move to the code part, which is very easy if we get this idea, and this is very easy question. So yep, now we will move to the code part. Okay, so let's move to the code part, and we can do this code part very easily. Basically, root, what is root? It's a pointer, it is pointing to 3 as of now, and it is like stored like this because like 3 has its children as 9 and 20 here, and then 9 has its children as null, and 20 has its children as 15 7, so it gets stored like this. So okay, let's first write the base case, that if at any point root is equal to null ptr, null pointer, then return 0. Okay, so this is not the base case exactly. This is the the condition that if the root is nothing, that it has null only, so like no point of running the whole function, the function gets closed right away. So now what we do, we can say it left depth, so left d we can represent. Okay, my bad, okay, so we can create this left depth. So how left depth is calculated, we can say left max depth, we can call this function recursively for the left part first, okay, and then in the same way if we want the right depth, okay, then we would call this recursively for right side of the tree. Fair enough? Yeah, fair enough. Okay, so then the function was to return 1 plus what was the function, that if we want for a node we are wanting the the max depth. So for a node, what was the formula? It was that max of, we can take left and right. Okay, so this was the main formula that we use. So from this we can basically get the max depth for every node, and at the final point it will reach 3 because this recursive call will eventually reach to 3 by moving 9, then 20, then 15, 7, and then above to 3. So basically the time complexity for this question is of n, because we visit every single node exactly once, so O of n is the time complexity. And for space complexity we can say it is O of h, because h is the height of the tree, because the recursion call stack, right? So if the tree is balanced, h is log n, and if the tree is completely skewed, like it's basically a linked list, so h is n, and we say the number of nodes. Okay, so this is the time and space complexity, and this was the whole question. So if you like the explanation in the video, please subscribe to the channel. Thank you so much. Bye bye.